Hi, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into rate limiting for my e-commerce platform, in-memory to Redis, fail open strategy, and per-endpoint limits. Let's go. Rate limiting is the countermeasure that makes every other vulnerability harder to exploit. If an attacker needs 10,000 attempts to succeed at credential stuffing, that's a realistic number against a platform without any protection. Rate limiting turns that into a 10,000 minute operation, 7 days. The attack becomes impractical. But rate limiting has a hidden failure mode on serverless platforms that most developers don't discover until they check their logs during an incident. In-memory counters are per function instance. On Vercel, with 5 active function instances, a users who request are distributed across those instances can make 5 times the limit before any single instance fires the counter. The limit is 10. The actual enforcement is 50. I built my rate limiter to avoid that with a store abstraction designed to swap from an in-memory map to Upstash Redis with a single environment variable. This video covers the implementation, the per-endpoint limit strategy, and why failed open is the correct default for an e-commerce platform. Why rate limiting? We have 4 attack vectors that they address. Credential stuffing. Automated scripts try thousands of usernames and password combinations from breached databases without limits. That's 10,000 attempts per hour from a single IP, even at a 0.1% success rate, which is realistic given password reuse statistics. That's 10 compromised accounts per hour. My limit, 10 attempts per IP per 15 minutes. That makes 10,000 attempts a 10,000 minute operation. Account enumeration, even with generic error messages, bulk enumeration via timing analysis remains feasible at high request rates. Rate limiting makes bulk enumeration time prohibitive. My limit, 3 password reset attempts per email address per hour. Coupon abuse. Automated script cycling through coupon codes can test 10,000 codes in minutes without limits. My limit, 20 coupon validation attempts per hour per user. Denial of service via expensive operations. Checkout involves a Stripe API call, multiple database writes, a tax calculation. A single IP making rapid checkout requests can saturate the server without volume limit. My limit, 10 checkout attempts per user per hour. The rate limiting algorithms, these are very important, okay? 3 algorithms, each with a specific trade-off. Fixed windows is the simplest. Divide time in the windows, 15 minutes, and count requests per window. 1 Redis key per window. Low memory. The vulnerability is the boundary burst. An attacker fires 10 requests in the last seconds of one window, then 10 more in the first second of the next. That's 20 requests in 2 seconds against a 10 per 15 minute limit. The burst is real, but the window won't catch it. Sliding window eliminates the boundary burst by tracking individual request timestamps and counting only requests within the last n milliseconds. No burst at window boundaries, but it requires over Redis memory, 1 key per request rather than 1 per hour. Use this for login and password reset where boundary bursts are actual attack vectors worth preventing. Thirdly, we have the token bucket. Token bucket handles bursty legitimate traffic gracefully. Token refills at steady rate. A user can accumulate tokens during low activity periods and spend them in a burst during high activity ones. It's more complex to implement correctly, and they're good for APIs where occasional bursts are legitimate. For this specific use case, at my current scale, my choice is the fixed windows for most endpoints, sliding window for login and password reset. In-memory versus Redis. The SVG shows the structural difference. In-memory map, 0 infrastructure cost, 0 latency overhead, works in development, but not shared across serverless function instances. It resets on cold starts, and an attacker can bypass it by triggering requests to different instances. The under-enforcement math. The limit is 10 requests per 15 minutes. Active Vercel instances, 5. User distributes the request evenly, 10 to instance A, 10 to instance B, and so on. 50 requests total pass before any instance fires the limit. Redis. These are shared across all instances and survive cold starts. INCR is atomic, approximately 5 milliseconds latency per check. Redis must be available, which connects directly to all fail open discussions on the next slide. My solution today. An abstracted store interface. The same interface with a different backend. The swap is one environment variable. I know the in-memory version under-enforces at scale. The abstraction means the upgrade is a configuration change, not a code change, and it is planned. The rate limiter implementation. The core function takes a key, a limit, and a window in milliseconds. It computes the current window number from the timestamp, uses that as a Redis key suffix so windows are naturally isolated, increments the counter, sets a TTL on first access, and returns whether the request is allowed plus the remaining count and reset timestamp. The key format is right there. Dimension is IP for unauthenticated. User ID for authenticated. Include reset in the response. Client can display a discount. Usage and server actions. Extract the IP from X forwarded for, call rate limit, check the result, return a structured error with retry after if blocked. The retry after value comes from reset at the timestamp when the window resets, right? The client uses this to show a countdown timer instead of a generic too many requests. Rate limiting architecture, 2 placement options, middleware, proxy, and server actions. Middleware runs on every request before business logic. It is the right place for global volume limits. Blocking obviously abusive traffic before it touches the server at all. A global limit of 500 requests per minute per IP stops volume attacks without knowing anything about what the request is trying to do. Server actions are business aware. They know the user ID. They can apply per user limits. They can check account tier. They can vary limits by context. All right. Log in with a known bad IP deserves a lower limit. A premium account might get higher checkout limits. None of that context is available in middleware. Both together is defense in depth. Middleware catches volume attacks from the network layer. Server actions catch targeted abuse of specific business operations. Both should emit 429 responses with retry after headers. Fail open versus fail closed. If Redis is unavailable, should rate limiting block all traffic or allow it? Fail closed. When Redis is down, block all requests. The result, your application goes offline whenever Redis goes offline. Redis's SLA is not your application's SLA. Upstash Redis has a 99.99% uptime. That's 52 minutes of downtime per year, possibly during planned maintenance volume windows. Any Redis connectivity blip takes your application down. Appropriate for nuclear launch code, financial systems with strict compliance requirements, authentication systems where any abuse is unacceptable, not appropriate for an e-commerce checkout that serves real customers who want to buy things. Fail open. When Redis is down, allow all requests. Rate limiting is temporarily degraded. Application remains operational. Log every fail open event. Alert on sustained failures. A sustained Redis outage means sustained degraded protection. You want to know immediately. My implementation wraps the rate limit call in a try catch. On any error, it logs a warning with the key and error message, then returns allowed true. The catch block is 3 lines. The logging is what makes it safe. You'll know it immediately when protection is degraded. Per-endpoint limits. A global limit treats login and product search as equivalent risk. They are not. Login, 10 attempts per IP per 15 minutes. High volume targets for credential stuffing. Legitimate users rarely hit this. It shows a countdown timer on 429. Password reset. 3 attempts per email address per hour. Enumeration and reset link. Flooding. This endpoint is rarely triggered legitimately. The checkout. 10 attempts per user per hour. Checkout involves a Stripe call and multiple database writes. Denial of service via rapid checkout is a real attack vector. Legitimate users almost never hit this limit. Coupon validation, 20 attempts per user per hour. Brute force coupon code discovery, 20 is generous for legitimate use. Product search, 200 requests per IP per minute. Read heavy but not free. Volume attacks on full text search. Legitimate users who hit this, perhaps a power user, should get minimal friction. And the dimension principle, IP for unauthenticated requests, user ID for authenticated. IP only limits can be evaded by rotating through IP addresses using a proxy. User ID limits survive IP changes. You're targeting the account, not the network address. The 429 response. A well-formed 429 response enables legitimate clients to back off gracefully. A bare 429 with no additional information causes retry storms. Clients that receive a 429 and don't know when to retry will retry immediately, potentially amplifying the load problem. The required header, retry after 847. This is a standard HTTP header, meaning don't retry for 847 seconds. Clients that implement this correctly will wait. Clients that don't implement it should be fixed. The informational headers, X rate limit, X rate limit remaining, X rate limit reset. These let clients display quota information, a progress bar showing how many requests remain, or a timer counting down to the reset. The response body follows my action result pattern. The message is human readable with a specific time. The retry after field is machine readable for the UI countdown timer. The action result pattern is OK's false, error as a message of code, rate limited, retry after 847, message, too many login requests, try again in 14 minutes. This message is human readable with a specific time. The retry after field is a machine readable for you. The retry after field is machine readable for the UI countdown timer. The client responsibility, show a countdown timer. Disable the submit button during lockout. Don't auto retry on 429. Log the event for monitoring. Testing rate limits. 5 test categories. The happy path. N-1 requests succeed. The nth is rejected. N+1 also rejected. Reset is at future timestamp. This is basic correctness. The window reset. Hit the limit. Wait for the window to expire. Assert N more requests. Succeed. Confirms the window counter resets correctly. Concurrent request. Fires N+5 requests simultaneously with promise.all. Assert exactly N succeeded and 5 are rejected. This is the critical test. Sequential tests will always pass regardless of race conditions. Only concurrent tests reveal whether the Redis INCR is truly atomic. Fail open behavior. Mock Redis to throw an error. Assert all requests succeed. Assert the warn log has emitted. Confirm your fail open path is operational, not just theoretically designed. Key isolation. Hit the limit for user A. Assert user B is unaffected. Hit the limit for login. Assert checkout is unaffected. Confirm the key format correctly isolates different users and endpoints. In production, monitor 4 signals. 429 rate by endpoint. Spike on login means active credential stuffing. Fail open events. Any sustained fail open means production is down. 429 by IP. Same IP repeatedly hitting limits across windows suggests automation. And 429 by user ID. Legitimate user hitting checkout limits may indicate a UX problem worth investigating. Rate limiting is defense in depth. In-memory counters under enforce on serverless. Each function instance has its own state. Design the abstraction for Redis from day one. Swap in one environment variable when traffic justifies it. Fail open for most production systems. Okay. Availability is more important than perfect rate limiting enforcement. Log every fail open event. Alert on sustained failures. Fail closed only for systems where any abuse is unacceptable and downtime is preferred over it. Per-endpoint limits, login, checkout, password reset, and coupon validation each have different risk profiles. Dimension by IP for unauthenticated. dimensioned by user ID for authenticated, survives IP rotation. Always return retry after. Clients that don't receive retry after retry immediately, amplifying load. Include X rate limit headers so clients can show quota progress to users. We test concurrency. Sequential tests always pass. Fires N+5 requests simultaneously. Exactly N succeed. Concurrent tests find Redis race conditions that unit tests miss entirely. For a client, rate limiting on this platform uses per-endpoint limits dimensioned by IP for unauthenticated and user ID for authenticated requests. The implementation is designed to swap in-memory to distributed Redis with a single environment variable. All rate limit failures are logged and monitored. The strategy is fail open. The platform stays available when Redis is unavailable. I'm Fleshed Out Thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing rate limiting for your own platform, store abstraction, per-endpoint configuration, or the fail-open strategy, reach out. I'm open to freelance projects and consulting. The full post is linked in the description below. Complete rate limiter implementation, the Redis store, and the per-endpoint configuration reference. Next in the series, proxies explained. Forward proxies, reverse proxies, CDNs, and why every request you make goes through at least one. I'll see you there.